Good morning, John here. Maybe you can see through here, maybe not. If you look in here, this is dry. The chemical's locked up in the plates. The battery's standing at 5.9 volts. It's actually a 6-volt cell. So what I'm going to do is apply current. And we're going to let this go. And I'll show you how the hydrate lets the water out with the electrical charge. So it's like a window that darkens in the sunlight and lightens when there's no sunlight. So we'll let this go and I'll be back. Meanwhile, I'm about to start this test over because the camera went light and dark. But here's a converted 5 amp hour alum battery running these lighting panels. This one on this side is real super bright, and this one is the next brightest. And it's drawing about 2.6 amps from this little 5 amp hour battery. And I want you to see the chart. It starts here at about 11.5, drops to the impedance, and then goes out, and we'll let this run out and we can watch what this lighting panel does. And I'm going to take you over here and show you something else. But anyway, that's your light right there. So it's pretty bright. Okay, I know this may be hard to see, but there's a trigger voltage with this chemical to where the current in the hydrate, once it's formed, becomes electrical between the plates, and that trigger current releases the water. And what I can see happening in the cell is it's starting to release the water, and you can see that down in this corner. So let me get this out of the way and now move it. And I know that this is kind of hard to see, but you can see the water is being released now from the chemical in this cell. And I'll move to the next one and then the next one. So that trigger on this current supply seems to be about 10.1 volts, and then it triggers and this will back down and the current will back down, and then it'll stay stationary with the water. So we'll let it go. You can see it's coming out of this one cell here right now, and soon the others will follow. So I'll be back. Now, one thing I want to point out is this is pretty typical of a hydrate battery, and you can see now that we're getting the liquid out of the crystal, and this is exactly what happens in a storage battery. Sometimes the outer two cells receive the charge faster than the inner cell because you have this impedance across the cell. It's not just one cell, it's in series. So I want you to see that. I want you to see exactly what's going on here. And so it's releasing that chemical right now. So let's go have a look at something else. Okay, in this dry crystal, I'm hoping you can see this, applying the trigger voltage to it. It's starting to release the water in the crystal, because this is pretty hard. And that's just hitting it with 10.8 volts at 1.2 amps is releasing the water in between the crystal to allow the battery to operate. So it can stay in a hard crystal like this for a long time. Now let's look at this. I'll be right back. Okay, the lighting is not real well over here, but if you look very closely, this is the crystal that's formed. It doesn't form on the side because the water evaporates and goes upward, but it's formed in between the plates, that crystal. And this crystal has monofilaments in it, and those filaments are what contain the water when the electrical charge hits it. Now, the chemical just standing alone in some experiments, as it dries out, is going to form this zeolite structure, and that's what it is. And you can see here that these are filaments. If you get real close, and you can, I can't zoom it in because my camera won't let me do that. Let's see here. But you can see the hydrate colors down at the bottom, and it's seeking water is what it's doing. So it's growing these nanotubes-like structures in the chemical, and this is what I'm trying to explain to you on there about a hydrate. So let's see if this one released any water, and we'll come back here. Alright. It looks like it is. It's releasing because this is now getting real soft around in here. So it's releasing the water. And it had the SO4 locked into the crystal, so it can't sulfate the plates. So giving it that current for a few seconds, let's see what it did. Be right back. Okay, so what I did is I placed it on this light that we built that charges with solar. And you can see when you release it, it stores the energy. And it stores it just like a capacitor in a way. It can go away and hide and then come back when you want to use it. But you must form it first. You must allow this to form overnight at a very small current. And then what you build is this electrical elm crystal, is what it seems like here. And now it's very soft and pliable. So it's releasing the water. It has released it, and we'll let this go and we'll see where this goes. But now let's go look at the alum battery that was formed like Ben's, which is a 5 amp hour battery. Okay, here's where we started over here, and I gotta watch out for this because I don't want the camera to go light and dark, because I don't want to ruin this and have to start all over again. A 1 impedance shift here, comes down, picks back up. This is a 2.5 ampere load, or 2.6 amps. This lighting panel, and you can see it's got them pretty bright. And I'm using the Mountain West just in the voltage, so I can track the voltage in the real world all the way down to where I cut it off, which is going to be at 1 volt. I don't suggest, people ask, John, can we take the battery? No. Do what you want to do. Take it down to 9 volts or 10 volts, whatever you want to do with the battery. I'm just making this to give you some explanations of what's going on. Be back. Okay, now we're back, and you can see that we released our hydrate. So you can see that it's an automatic switch to lock up the water. So what actually is happening here, through very close examination, is the sulfate that normally would attack the lead plates is being locked up by the hydrate crystal in between the plates. Then the electrical charge allows the liquid to come out. Now, I've used more of a crystal formula than most people because I've packed it in there. And what I want to say is, if you're in the aqueous where you're all liquid, you probably won't see this, although some did, that they thought that there wasn't enough water in the cell. That's because it's locking it up. And when you apply the current to it then to charge, it's going to let that water out of the crystal, out of the hydrate. And so what you've actually built is a switch to lock hydrate and a switch to let the hydrate out between charge and discharge. And that's a good thing, because you don't want the plates to sulfate. And I'll be back. Okay, once again, I'm going to be very adamant about this. What you're actually looking at here is a switching crystal that can go from solid state to aqueous, meaning the water comes out and combines and forms the battery. So the sulfate goes away in the lead here. It's locked up in the hydrate crystal, and so it can't get on the plates. You can only deplete the solution. So let me go over this one more time with all of you people, that there's a trigger current and voltage that lets this happen once the formula is balanced in the battery. And there's a few people on the group that have seen this already by adding water when they think the water's low. No, that's not what it's happening. What's happening is that the water, the sulfation is being locked up in the crystal, and so the level of the water in the alum battery goes down. When you apply current then to charge it, the sulfuric acid that's locked up, the SO4, which is now in balance with the alum, is released and produces water, just like you see it here. And nothing harmful about this, touching it at all. Anyway, let me take you back and show you this one more time, because I want to make sure that you understand it. Okay, applying power to this crystal, right, with current, allows it to release the water that's in the structure. It's an electrical crystal is what you have built when you balance it out. It works like a window that's sensitive to light. It changes from dark to light. And that's exactly what you got here in a solid state form right here. Because you move it back and forth. So, the way to test this then, the theory of it, is to allow it to form and allow it to crystallize and then allow it to bring it back. But if you leave it in the air like this, it's going to want to grow and release everything. And so that's why we cover them, because we want them to end up where the crystal's like this. It locks it up, and you see it's like a gel almost, and the moisture stays inside there. You can see the water droplets on top here. And it happens with every one of them. Where the material gets out, it starts to crystallize and grow these nanotube hairs of alum. But it's not the same as a sulfuric acid crystal. It just doesn't work that way. Alright, let's go over here and look at something else. Alright, once again, this is totally dry. And it's grown from the bottom up. It's just a powder now, or what you would call a form of zeolite, because that's exactly what's happening here. It's growing zeolite. Of course, that zeolite is not found in the natural mineral zeolite. So it's totally different. It's a mimic of it, but not quite it. Anyway, they will retain some power at a small level, see, this is way too much current for this crystal because it's just dried out. And you'd have to saturate this and get it to go in its bath. Sort of like what's happening in here. That's why we leave them to see exactly what's going on. The moisture is contained inside here, and all the foreign material, it just grows a crystal upward like this. Sort of looks like angel hair, basically. Little tubes that evaporate the hydrate water out. So I want to make sure that you understand what you're dealing with when you build this battery. You're dealing with a switch that can go between the sulfation process and the water process, not letting the sulfation attack the plates. So I'll be back. So now what I want to do is I want to show you that once the water comes out of this crystal, and this is very soft now, you're going to have your power. And you're going to keep that power until the crystal goes the other direction and locks everything up again. So that's why you want to put a cover on these, to keep the moisture inside the crystal, because you don't want that just going out into the air and disappearing and forming these tubes that are just actually doing nothing for you. But when they're in between the plates and they have a basis of being electrical, they can switch back and forth. They can go between aqueous solution and crystal solution. Be back. Okay, we can see where this 2.5 to 2.6 ampere load is now on this crystal cell that's been converted. And we're down at about 4.09. Of course, when you're dealing with a crystal battery, you may be dealing with something that just sits there and sustains this for long periods of time. And believe me, if it was dark, this is a lot of light. So no matter where this battery goes, it's going to always do the same thing over and over by charging and discharging. It's going to remove some of the liquid, because this is exactly what a battery does. When the two plates become the same, you have no more battery. But in this case, this can lock that up, save the lead plates, which it seems to do here in all the experiments, and probably sustain this. You can see two impedance shifts, one here, then it comes down and goes on its. Okay, back again. I'm sorry I ran out of memory. I mean, I want to make sure that you understand these hydrates and how they work in the lead acid battery when you convert them. So there's your water, and that's where your current's going to stay, just like a capacitor, just as if I had a capacitor. So if I take this away, the chemical now will start to absorb back into the plates, because remember, it's a switching mechanism. But meanwhile, while this is doing this, I can draw all the power I want from this. But I'm doing a different test over there where I would run this cell. But I think you understand what I'm getting at here with the chemical. And I want to make sure that you understand that the water's locked up. And that's what keeps it from sulfating the plates. That's why the Elm battery works in these car batteries that you convert. As the sulfation gets transmuted basically into the Elm crystal. And so the plates get cleaned off, and then the battery is restored again. And there's some real good examples on the internet of that on the Energy Science forum that I've seen in batteries that had 1 volt, and I just want to thank those people for doing it, and don't think that I'm not paying attention to you. I am. And I'll write as soon as I can about the good work everybody's done. And I also want to thank you for the support on the forum once again. And I'll be back with just something more here to show you, and I'll be done with this video. Okay, here we are again. We started out here, and this has been over 3 hours now, and now it's going right down to where a crystal battery works, and it'll sustain that right there for long periods of time. So I just wanted you to understand what's taking place in here, in this battery, and that's switching between the aqueous and the crystal. So you all have a good night or a good day.